Hello, my name is Ari Barastiano and I want to tell you today about random sets. What I'm going to do is describe the basic definition of what is a random set, go over several examples, and set up start this series of videos that eventually lead to understanding the paper that I wrote with Francesca, the econometrical paper from 2008. The link to it will appear at the bottom of the video. So I'm going to assume that you know probability, that you know what random variables are, and that will be the starting point, and then from there we'll go on to talking about random sets. So again, the starting point is the probability space. We have omega, and we have the sigma algebra, this fancy F, and a probability distribution P. Okay, a regular random variable, as you may know, is a mapping X from omega to, let's say, RD. Okay, so we are talking about real valued or real vector valued random variables. And for it to be a random variable, it has to be measurable. So we will look at X, okay, the inverse of X minus 1, okay, of some measurable set in RD, so let's call set A, okay, and that will be all the omegas in omega, such that X of omega in this mapping, okay, is in A. Okay. This is a set or subset of omega. This has to be a member of the sigma algebra. Okay, and that's a measurability condition which says that X, or if it is satisfied, then X is a random variable. That's the basic. So now we want to look at random sets. Okay, so instead of looking at a random variable or single-valued random variable, we are going to look at sets. So I'm going to define two subsets of RD. So we will call this F, okay, to be the collection of closed subsets of RD. Okay, and this script K, I'll call it like that, the collection of compact subsets of RD. Okay, so now in order to define a random set or set-valued random variable, that's another way to call it, we are going to say, and I'm going to use lowercase letters for the regular random variables, the point-valued random variable, and capital letters for the set-valued. Okay, so that will be a mapping X. Okay, again from omega, the same omega, but now we are going to go and have values, okay, in F. Okay, so for every small omega in omega, we will match a subset, a closed subset of RD, rather than just a point in RD. Okay, so this will be, okay, so let's call it definition, okay, is a random set, okay, if, and now comes the measurability condition, which will be a little bit different, okay, for all set K inside this fancy K, okay, so every compact subset of RD, okay, X, okay, maybe I should do like this, so you know it's a capital X, X to the minus 1 of K, set K, this K, which is defined to be, it's defined to be okay, this fancy light board, okay, all the omegas in omega, okay, such that x, capital X, of omega intersection, okay, with k, this set k, is non-empty. Okay, so that set is now in script F, in the sigma algebra. Okay, so notice that we make this measurability condition not for any closed subset of RD, but for the compact set of RD. And that is done in order to avoid some measurability or problems, and to make some of the functionals that we would like to work with later on to be random sets or random variables. And so there is some reason. So you can look at Molchanov's book, and we have some comments on that in the paper, but the best source is Molchanov's book, which I will put again in the comments for this video, okay, in the description of the video. Okay, so that's the basic definition of what is a random set. Okay, so now let's look at some examples. The first one, which is almost obligatory example, is that let's say that we have x, okay, lowercase x, to be a regular or pointwise random variable, okay, and then define capital X to be just this small x. Okay, I just put curly brackets. Okay, what it means is that this x omega is equal to the set that includes the point x of omega. Okay, so that will be a random set. That's a very easy example. Okay, another more interesting example will be the following. Let YL and YU be two random variables, okay? And the probability that YL is less than or equal to YU is 1, okay? So they're distributed, these pairs, okay, is such that their joint distribution is such that this probability is equal to 1. Okay, and now let's define this set, random set capital Y, okay, to be the interval UL, UU. Okay. Okay, and again, what it means is that Y omega is equal to the interval lower YL or YL, sorry, of omega YU of omega. Okay, so that's another example, okay, of how to construct a random set. Yet another example, okay, so this Y is always in, is a set, is a closed set in our one. Okay, let's see another example. Okay, so this is example 2. Another example will be the following. Okay, so now let's have, in addition to UL and UU, okay, YL and YU, we also have X, small x, okay, be 3 random variables, okay, and define now Y, okay, to be the following set. It's going to be, okay, all the numbers, all the pairs of numbers, okay, I'll call them, let's say, A and B, okay, such that A is in the interval Y lower, Y upper, okay, and B, okay, is equal to A times X, So again, translating it into the omega notation, it means that y omega, okay, is the segment in R2 connecting the point YL of omega comma YL omega times X omega. Okay, that's one point. Let's use a curly, and the point Y upper omega comma Y upper omega times X of omega. Okay, those are 2 points, and let me clear some space. So to wrap it up, let's draw this example of random set. For a particular omega, here is U lower of omega, which is lower than the U upper of omega. And again, for the sake of example, let's think that X is a positive number, so this will be U lower of omega times X of omega. Okay, suppose this is 1, this is 5, X is equal to 1, so again this will be 1, and okay, or maybe X is equal to half, so this is 1 times half, and this is 5 times half. Okay, so this is Y upper omega times X of omega. Okay, and the first point, okay, is this one, will be this point. And the second point, okay, is this one. Okay, here is the segment. Okay, and for this particular omega, this is the random segment in R2 that we will get. Of course, for a different omega, the segment could look like this. There will be maybe X is negative or anything like that. It can be downward sloping and so on. So we will get many random segments in R2. Okay, and that example will be important when you look at the paper with Francesca that we wrote in 2008. Thank you for watching.